Hello, my name is Shelvena Lidis, and now I will start with the problem statement. As we know, material will face several hidden risks in high temperature environments. Firstly, material often expand or warp unexpectedly, and without the proper data, an engineer will risk on designing structure that may buckle or collapse, especially in industries like aerospace and automotive. Next, when heat and tension act together over a time, a creep deformation becomes a silent threat. Even a strong metals can eventually bend or crack and causing unexpected failures in a turbine or a pipelines. A heat also can change a material's internal structure, and these changes are not always visible but still can weaken a tool's or a machine parts if we are overlooked. Next, the way stress is applied affect materials differently in different directions. This anisotropic behavior complicates a design and making a prediction to more difficult. Lastly, a thermal shock, especially in brittle materials like glass or a ceramic, can cause an instant failures. Sudden temperature changes are often underrated, but they are a real threat in a design.
Hello, I'm Farah. In this part, I'll be sharing the objective that focus on understanding how materials deform under thermal stress. When materials are exposed to different temperature, the dimension can change. These changes can lead to deformation, sometimes temporary and sometimes permanent. This study aims to carefully investigate those effects, especially we have four objectives. First, to analyze the thermal expansion or contraction of selected materials by heating or cooling them. We'll observe how much they stretch, shrink, and wrap. Second, to determine the distribution of stress and thermal strength within this material as the temperature changes. Some areas might stretch more than others, creating internal stress. Third, to identify the critical temperature ranges that cause permanent deformation or even failure. Knowing this helps us avoid operating conditions that could damage the material. And fourth, to generate valuable thermomechanical property data. This data is essential for predicting how materials will behave in environments with repeated heating and cooling cycles.
Hello, it's me again, Shelvena Lidis, and from this issue that have been mentioned before, we propose 5 key of hypotheses, which the first one is the material have different rates of thermal expansion. For example, metal usually expand more than ceramic, and knowing this will help an engineer to prevent a dimensional issue. The second one is material that under continuous load and heat can slowly deform with the process called creep. This is common in high temperature equipment like steam pipes. Next, the heat will change the microstructure of materials where it directly affecting hardness and strength, and that's why treatment are used to improve tools. A part of that, metal can and composite don't behave the same in all directions, and that's why this direction-based behavior must be considered in thermal stress situation. Last but not least, a thermal shock can cause a crack, especially in brittle materials. So, based on this hypothesis, it helps us for better understanding and to predict the material behavior under the heat. And that's all from me. Thank you.
Assalamualaikum and hi everyone, my name is Amnia Afika and I will begin by presenting the analysis of information and data for our mini project. First, we'll explore thermal expansion and contraction. This refers of how material change size when exposed to heat. For example, metals like steel and aluminium expand uniformly, while polymers or composites may expand unevenly, which can lead to internal stress or damage. That's why bridges and railways have expansion joints to prevent structural failure due to heat. Next is the creep deformation. This is a slow and permanent change in a material shape when it is continuously exposed to heat and pressure. It often occurs in high temperature components such as steam pipes or turbine blades, which can sag or crack over time if not properly designed with creep resistance in mind. We also analyze microstructural changes. Heating and cooling cycles can alter the internal structure of materials. For instance, metals can become harder or more brittle. Plastic may soften or degrade, and ceramics can develop tiny cracks. These changes affect the material strength, durability, and performance. Then, we look at the anisotropic behavior, which means a material responds differently depending on the direction of the force or heat applied. For example, rolled steel is stronger in the rolling direction because of how its internal grains are aligned. This is especially important in products like airplane wings or car panels. Lastly, thermal shock resistance is the material's ability to handle sudden temperature changes. Brittle materials like glass or ceramics can easily crack when going from hot to cold quickly. For example, a hot thermos filled with cold water might shatter if the material can handle the stress.
Hi everyone, my name is Sabrina Fernandicol, and today I'll be talking about thermal expansion. Thermal expansion is the tendency of materials to increase in length, area, or volume as the temperature rises without changing their phases. When things heat up, their particles move faster. The forces holding them together get weaker, and the materials start to expand. How much it expands depends on the material itself, and we measure this using something that we call as the coefficient of linear thermal expansion. This predictable behavior is really important in engineering because it helps us to design structure and components that stay safe and work properly even under different temperatures. Creep is a slow and permanent deformation that happens when a material is exposed to high temperature for a very long time. It is a big concern in high temperature systems like boiler, pipelines, and superheaters. As the temperature and load increase, the rate of deformation speeds up, and eventually, the material can fail if it can't handle the stress anymore. That's why choosing material with good creep resistance is so important when designing for high temperature environment. Thermal stress alters a material's internal structure, affecting its behavior. High temperatures cause allotrophic transformation in metals, softening plastic, breaking down ceramic, and causing delamination in composites. These changes affect performance and safety, affecting the material's lifespan and safety. Anisotropic materials have properties that vary depending on the direction. In composites, for example, fibers are aligned to boost strength when it is most needed. Processes like rolling or layering can enhance this directional behavior, which play a big role in how we design components. So engineers need to understand and consider anisotropy to make sure structure stays strong and reliable, especially in fields like aerospace, automotive, and construction. Thermal shock resistance is a material's ability to handle sudden temperature change without cracking or breaking. For example, pouring cold water into a hot glass thermos can cause it to shatter. Strong materials like porcelain tiles and forged metals are better at handling these shocks. That's why blacksmiths and engineers use materials like it or special ceramics and often apply controlled heating method to make sure that this material stays strong even in extreme conditions. Thermal shock.
Now, let's talk about why this study matters. The finding from our research on the thermomechanical characterization of materials, dimensional deformation under thermal stress, have several important implications. As first, improve design and engineering safety by accurately predicting how materials expand, creep, and change at different temperatures. Engineers can design safer and more reliable structure. This is especially critical in industries like aerospace, automotive, and construction, where temperature changes are constant and can lead to dangerous situations like buckling or material failure. For example, in bridge or railway construction, engineering intentionally includes small gaps or flexible joints to allow for thermal expansion. Second, the material selection for high temperature application. Every material behaves differently under heat. Metal, plastic, ceramic, and composite that are expand and weaken at different rates. Our research help manufacturers and engineers choose the most suitable material for every application, improving both safety and performance. Longer service life and improved maintenance strategies. Over time, heat causes materials to slowly deform, creep, and repeated heating and cooling can lead to thermal fatigue and cracking. Understanding these behaviors means industry can plan better maintenance schedule and avoid unexpected equipment failures. And fourth, the study support the development of new high-performance materials by studying how heat affects microstructure, strength, and flexibility. Material scientists can design material with higher thermal stability and better resistance to fatigue. For example, adjusting the fiber orientation in a composite material or tweaking an alloy chemical composite can make it more resistant to cracking and deformation in extreme heat. In short, the implications of this study go far beyond the lab. They impact the way we design, select, and maintain materials and structure in some of the world's most demanding industries.
In conclusion, this study shows that materials behave differently under thermal stress based on their physical and internal properties. Understanding factors like thermal expansion, creep, microstructure, anisotropy, and shock resistance help engineers design structures that are both safe and long-lasting. By applying this knowledge, such as using expansion joints in railways or bridge, or flexible components in buildings, engineers can prevent failures and improve performance. Overall, these findings are essential for industries like aerospace, automotive, energy, and construction, where thermal conditions are constantly changing. So that's all from us. Thank you.